Let's close the door. Thank you. And yeah, let's get started. Last time we continued our discussion about bandpass low-pass transformation. We discussed some interesting examples. And in the end, we start discussion about heterodyne, about example with heterodyne. And in the very end, I made typo because I forget minus sign. Because I forget this minus sign that comes from outside parentheses. And yeah, if we take minus outside, minus for wait a second. Okay, let's try to understand everything from the beginning. Different result at the moment. Task number 2.5. So, and let me find the task itself. So, this is our task. And we have the following situation. That consider two signals, xt and y of t. Xt given as x0 times c function, and yt given as y0 times c square. And we know that x0 and y0 are real valued and positive. Then we need to draw the Fourier transform for x of f and y of f of these signals in time domain, of given signals in time domain. So we did it, and if we calculate inverse Fourier transform, direct Fourier transform of this signal, we can first of all we can represent this signal in the form that we have in our table of Fourier transforms, and then we see that we have in frequency domain for first signal we have rectangular pulse with amplitude x0 times f1, or we can write it as x0 times t. And for second signal, have a c-square function. After Fourier transform, you will get a triangular shape function. And we made replacement f2 equals to 1 over 2t. And after we calculated Fourier transform, we get that we have signal or spectrum in frequency domain y0 times 2t times triangular function of f times 2t. It was our signal. And maybe we can also make a picture of this signal, because we made it last time. So as a result, we had to get something like triangular shaped function. So, and also say that how can we represent this triangular, or we can rewrite triangular function as triangular f divided by 1 over 2t. 1 over 2t. So this length, which corresponds to, or we can write it on the positive side, 1 over 2t. And triangle function goes from 1 minus 1 over 2t, 1 over 2t. Amplitude of this function will be y0 times 2t. This is our y of t. Okay. Yep. Then next step that we had to do, we assume that xt and yt are to be mixed into an intermediate frequency range first. And we do it by multiplying x of t by cosine function of intermediate frequency and y of t by sine function of intermediate frequency. And we assume that intermediate frequency equals to 1 over t. So we try to show how the signal looks like. So we have the following expression, how we perform this transformation. We take our signal x of t and multiply by cosine, y of t by sine. So, and we can write that this is how it looks like in time domain. And if we go in frequency domain, we can write that we use the spectrum of our signal times, and then we have Fourier transformation of cosine and sine functions. So we have x of f and convolution with 2 delta pulses. So we have to shift our signal to the right and to the left, and then also we have to multiply by amplitude square root of 2 over 2. Take our original rectangular pulse, shift it to the right by the frequency 1 over t, shift it to the left by frequency minus 1 over t, and normalize by scalar square root of 2 over t. So this is our result that we get. This is so-called real part of our signal for intermediate frequency. Then we consider second part. We have y of f convolution, and then we have 2 delta pulses. But both delta pulses, they imaginary, because we assume that they have shift equals to 90 degrees. So, and let's try to analyze what we have here. So we have a complex number in denominator. Want to move it up, we multiply and divide by complex number j. As a result, this j times j gives us -1, but we also have to take into account minus in front of this expression. As a result, minus times minus will be plus, and we have positive spectrum for positive frequencies. And it was typo last time here because I forget to take into account this minus outside expression. And for second part, we have negative. We have negative amplitude, and we get that we have amplitude y0 times 2t times square root of 2 over t. Now it's correct result. Okay, any questions to this part, to this point? And again, just want to point your attention that it's very easy to forget some scalars, so please careful when you're operating with them. Okay, let's go further. And then we need to draw. Okay, so we come to next part where we take our signal at intermediate frequency and we mix up it again to the bandpass range. How we do this? We take our intermediate signal at intermediate frequency and multiply by cosine frequency. So, and we need to draw this signal at the bandpass frequency. Let's try to do this. Have that the bandpass of E equals to, and then we have at intermediate frequency E times cosine pi delta f, no, f delta t. And we need to draw spectrum of bandpass signal. So, and here we can write again, we can try to represent or find first expression for spectrum, bandpass range. And no, this is spectrum, it's function of f. We write it as u frequency of f and we know how it looks like. Convolution with, then we have convolution of this cosine. And this convolution given as 1/2 delta f minus delta f plus delta f plus delta f, our function. And we also know that okay, yeah, we have this range of delta, but let's leave it as it is. It equals to 9/t, 9/t. So, and what we get, yeah, we have this spectrum, and we have to shift it, because this is cosine, yeah, we have to shift it to the right and to the left by the same quantity, 9/t. I think I will show you not exact picture, but because otherwise it will be by 9/t. But let's show that somewhere on this axis we have frequency. Okay, maybe not. But let's say have 9/T. And then I also have to by the same point on the negative range. We have minus 9/T. Okay. And now our central frequency, and we move our signal from intermediate frequency to 9/T. And so instead of 0 frequency, now we get 9/T. I have to show, I can write that we have now, we have center of one rectangle will be at 10/T. Center of another rectangle will be at 8/T. I have to show rectangular functions. So, first rectangular, have second rectangle. Okay, but also I shift, because I have second delta pulse, and I shift by frequency minus 9/T. Oh, range, and I also have to specify these two rectangular functions. Like this. And what will be the amplitude? What will be the amplitudes of each rectangular function?
Sir, you have missed two from, there should be 2 cos 2 pi f delta t as per the question.
Oh, no, I didn't miss. I just have different version of this task. Yeah,
Okay,
it could
actually,
happen that Dr. Wolf updated tasks, but in my version I have cosine. But you can just change it correspondingly to the way
there is no 2 cos. There is no 2 cos in that.
Yeah, it's what I say, that it could be that you have updated version.
Yeah. Oh.
So just change it correspondingly to the, because in my version I have cos, and I just write it.
Okay, fine.
As I have. But thank you for this information. Okay, yeah.
Hello, Professor.
Yes?
Is 9/t given in the problem? Or like, how did you find it? F delta.
Yes, I mean, we guess that we have a spectrum as rectangular from the beginning.
Okay, thank you.
Okay, if to be correct, we don't have this information, but we have found that we have rectangulars. How did you find this 9/T? Okay, you start to answer questions to others. It's very good. Yeah, I cannot show you my notes because this document camera doesn't translate WebEx, but it's given. First of all, we know how let me go to the beginning of this time. We know how signal in time domain looks like. This is x0 times c function. It is given. And then we calculate Fourier transform of this signal. And we find that in the frequency domain, there's nothing else as rectangular shape function. So we find this. And then, first step, we perform a transformation for intermediate frequency. And now we do second step. We transform by given frequency 9/t transformation to the carrier frequency. And for this reason, I have written this 9/t because it's given. And what I do, I just shift one copy to the right by 9/t and copy another and shift another copy by frequency minus 9/t to the left. And my next question, yeah, and we, of course, all answers will be all answers that are right about they're related to this form as written in my case. Because, yeah, unfortunately, I have a slightly old version for tasks. And if you check online, probably you see slightly different version. But conceptually, nothing changes. You will have just slightly different scalars. Okay, and what will be the amplitude of a rectangular shape window? Not so deep, actually. It's not difficult. F naught, x0, okay, then yeah. Square root of 2 and by 4. No, we have, okay, we have x0 times t, square root of 2. But it was amplitude for pair of rectangular windows before. And then we divide it for 2, because we multiply by 1/2. Have over 4. Okay, and but if you multiply by 2 cosine, then of course you don't, your amplitude doesn't change. It will be divided over 2. Okay, fine. And it was part of bandpass signal, real part. Okay, and second part. Also, we have another. I also specify frequency 9/t minus 9/t. And then have to shift second part. Have one component at frequency n/t, another component at frequency 8/t, and at positive 10/t, we have triangular shape function. I repeat this also for negative. Minus 8/t minus 10/t. like this. And also, I write that it's our imaginary part of and our amplitude will be phi 0 times, then we have 2 times square root of 2 over 4. Okay, the same. And also we call that if we consider everything what on the right side in positive range of frequency, everything what is on the right side from carrier frequency, call as upper sideband. And everything from the left from the carrier frequency in positive range we call as lower sideband. And in amateur radio, it's very common technique when if you communicate with someone, when you transmit, you use upper sideband, and when you receive something, you use lower sideband, and it allows you to transmit and receive information at the same time, using only one resource frequency resource block for both directions. So you don't need to have two channels. Okay, what else we need to find? It was part. Assume that the final bandpass signal shall not contain spectral components below frequency 9 over T. And what we must done is bandpass signal, make it possible. Again, assume that the final bandpass signal U subscript by P of T shall not contain spectral components below frequency 9 over T. Typically, what must be done with our signal on carrier frequency? A very simple answer. If you don't need some spectral components, what's your actions? Filter, that's all. Apply bandpass filter. So sometimes we ask you very cool questions. Find, find the equivalent low-pass signal where the transform is to take place with regard to the frequency 10 over T. So we assume that we don't have any components below 9 over T. And now we perform low-pass transformation of the remaining parts. So assume that we applied kind of selected only upper sideband. Yes. Strictly speaking, we need filter that goes from 9 by T and then goes to plus infinity. This is just as this is just example as it could be. But idea that we need to select everything what goes above. Okay, and now we need to perform low-pass transformation of this signal. We don't have any components below, and And also we perform transformation with respect to frequency 10 over t. So again, we remove negative part, we shift our signal to the right, to the left, and we normalize it. Normalize by multiplying square root of 2. Result, we get that we have rectangular shape window, shape spectrum at frequency 0. Spectrum goes from -1 over t, 1 over t. So we have amplitude x0 times capital T and over 2, because when we multiply by square root of 2 and divide by 4, we can cancel 2. And then we have, this is our signal L of f. Also, we have second signal. For second signal, we have only a triangular shape function. And we have times 2t times square root of 2 times square root of 2 and divided by, we can simply cancel, right? Y0 times t, our UL of f of L, U1 of L. So, yes. Yeah, here. Yeah, but I mean, because we say that at part D, we assume that we remove everything what goes below 9 over t. Then we perform bandpass low-pass transformation. Yeah, just directly try to get low-pass transformation as if you would perform transformation directly with respect frequency 10 over t without any intermediate steps. We take into account that we have for second signal, it was imaginary, so it already contained imaginary number, and we have to multiply by j. Yeah, we have to also multiply by j amplitude. And let's check what we need to find. I think that's all for this part D. Then we go to part E. So at part, not E. Part was for this transformation. Now we go to part F. So the approach treated so far is called, okay, this approach is called as superheterodyne up conversion, which steps are required for superheterodyne down conversion. Assume that the spectral range below 9 over t may also contain spectral components due to noise, neighboring channels, and so on and so forth. Okay, I will just show you how the receiver will look like. First of all, we have our signal bandpass range. Take our signal and we perform selection of first for us band range of frequencies. Do we want upper sideband or do we want lower sideband? After we perform first step for of this heterogeneous receiver, we multiply by cosine 2 pi f delta t. And then perform low pass transformation. I mean, nothing special. You just take this amplitude and multiply by square root of 2. Because again, you remove one of 2 halves. This is just typical low-pass transformation. And then you have 2 times square root of 2 by, again, square root of 2 and divide by 4. And then it will be your y0 times t. Oh. No, here it's low-pass filtering, because its transformation will be on next step. On next step, we quadrature. We multiply by square root of 2 cosine y f delta t. Then we have another low-pass filter. Then we get real part, and for another branch, apply by square root of 2 sine 2 pi f delta t. Get imaginary part. Sorry, we multiply by minus 2 sine f delta. At upper branch, we get x of t. At lower branch, we get y of t. Okay, yeah, that's all for this task. And are there any questions? Just let me know if you have any questions. And now we go to next section. Now we come to discussion about correlation theory of deterministic signals. So we consider the following signal. We have signal u1 of t and u2 of t. u1 of t is a signal that contains a rectangular shape function, and y of 2 of t contains 2 rectangulars. One is positive amplitude, another one with negative amplitude. And what we want to find, we try to find the autocorrelation function. Yeah, what's the question? Sorry? Okay, yes? Yes, this is real part. And below we have imaginary part. Yeah. I mean, this is just the same. We select real and imaginary part separately using cosine and sine generators. Yeah, this is the idea. This is called also quadrature demodulator. Okay. More questions, or should we? Okay, more questions. No, this is not bandpass. It's a filter. It's filter. It is low pass filter. Because after transformation, you will have, after you multiply by cosine, you will have, okay. When you have such signal, when you multiply, for example, this one, remember that what you do when you multiply by cosine, you shift something to the right and something to the left. And then when you multiply by cosine, one copy you shift to 0, and another copy you shift to the frequency 18 over t, I think. Yeah, if we perform with respect 9 over t. So you will have some components at very high frequencies, and you need to remove them. And you remove them by applying this low-pass filtering. For this reason, we have this second low-pass filter. And first bandpass signal selects band that you want to work with, upper or lower band. For this reason, you need two filters, even 3 filters, because after this, after you select real or imaginary parts, again, you need to remove components with higher frequencies. Yeah, for this reason, you need 3, even 4 filters. Yeah, no problem. If there are any questions, please let me know. Okay, and let's go back to our task. So we have 2 signals, u1 of t and u2 of t. We need to determine the autocorrelation function of each signal, and we need to plot the corresponding figure. So let's try to do this, try to solve this task. Task number 3.1. Oh, I have to switch to. So we have 3.1. And we have signal 1 of t equals to u0 times rectangular function minus t over 2 divided by capital T. So, and then we have second signal of t equals, and then we have difference between 2 rectangular functions. We have u0 times rectangular function minus t over 4 divided by t over 2 minus u0 rectangular shape function minus 3 over 4, and we divide by t over 2. Okay, first part, usually that we need to plot each signal and try to analyze how it looks like. Try to plot first signal, u1 of t, and have 0 origin and so. Our signal shifted by t over 2 to the right, and the whole duration equals to capital T. Let's say this is capital T, and our rectangular function, our rectangular pulse, goes from 0 to capital T, and the middle of this pulse at t over 2. Okay, and for second signal, we have 2 rectangular pulses. First pulse goes from 0. No, first we say that it centered at t over 4, and it has duration, or it has width t over 2. So we can conclude that it goes from 0 up to t over 2. It will be positive part. Maybe I use different color. It's green color, and this is our positive part from 0 to t over 2. And then we have second rectangular pulse that is centered at 3t over 4, and it also has duration t over 2. So this is how it looks like. And it's our second u2 of t. And we are in time domain, t, and amplitude equals to u0. Okay. Now we need to determine autocorrelation function for first signal and for second signal. Phi y1, phi 1, energy, and tau. So we consider we need to calculate this autocorrelation. And let me find expression for autocorrelation. Okay, yeah, here we are. And we have the following expression. Now I forgot where's pen. We have interesting situation. When you calculate autocorrelation, we need to find the following integral. So correlation k times k of tau, we can write as integral from -infinity to infinity of signal uk of t times uk of t plus tau times dt. And it can be written as integral from -infinity to infinity of uk of t times uk of t minus tau, because we write it as a convolution integral, times dt. And it is nothing else as convolution between the signal uk of tau, this signal uk minus tau. So, and now let's try to understand what we should do. I will plot our original signal u1 of t. It's just rectangular shape function, u1 of t. And the convolution means that we have to calculate we have to calculate convolution between this signal, the slightly modified version of itself. And what it means that we modify. We shift our signal to the right or to the left, depending on the value of delay that we try to evaluate. This is our signal u1 of t. Then below we have signal u1 of t plus tau. And then where we have to shift our signal for positive delay. If we choose any positive value for delay, if tau equals to 1, 2, 3, and so on and so forth, you will have expression, let's say u1t plus 10 of some units, 10. And where you shift if you have plus something? To the left. Yeah, but for me, this is right. But you're right, yeah, we shift to the left. So we go to the left if tau greater than 0. If we say we try to analyze for tau equals to 1, 2, 3, we start to move slowly to the left. If I ask you what happens for tau for tau smaller than 0, you will have something like u1 t minus 5. And minus 5 means that you shift to the right. This is very important observation, that for positive delays, you have to shift your copy of your signal to the left, and for negative delays, you shift to the right. Okay, and now we need to calculate overlapping area between the original signal and copy for different values of delay. This is what we try to do. And of course, you can see that we don't need to evaluate infinity many different points. We just need to evaluate what happens in the range of our signal. Because if copy will be outside this range, for example, like this, yeah, this is for delay, something like greater than t/2. What happens in this case? What will be the result of correlation if this is our original signal, this is our original signal, and then this is delay greater than t/2? What? It will be 0, because they not overlap. There is no any correlation. What we do, we have our signal. For 0 delay, they match each other. But when we introduce delay, second signal copy start to move to the right or to the left, depending on the value of delay. Is it positive or negative? And then if you take a very large delay, then they don't overlap anymore. If you take, for example, 10t delay, then there is no overlap. As a result, correlation equals to 0 for this specific case, because they simply not overlap. And now we try to analyze more precisely, taking special points. Yeah, let me put it back. So this is state. This state when we have that they match each other corresponds to the case tau equals to 0. And maybe below I will plot resulting correlation. Resulting correlation. And it function of delay. And we denote it as phi 11 tau. So when delay equals to 0, 0 point, it corresponds that our pulse matches exactly our original signal. And what will be the result of integral in this case? I have to also specify amplitudes for u0 and u0. And duration is t/2, if I'm not mistaken. No, it's not t/2, it's t. T, yeah, thank you. T. So what will be the result of integral? 0 squared IT. Or not? No, at one point. At point tau equals to 0. It will be it's not line, it's just 1 point. What you do, you need to multiply these two functions element-wise. And then you need to integrate over the whole range from -infinity to infinity. When you multiply two amplitudes, you will get u0 squared. And when you integrate from -infinity to infinity, you actually integrate only in the range from 0 to capital T. Yeah, that you just multiply. It's area of rectangular pulse. You just multiply by duration, which is equals to t. And you get u0 squared times t. u0 squared times t. So, and agree with me or not? Be difficult. It shouldn't be difficult. Why you looks confused? Or is it fine? Okay, so this is for point for tau equals to 0. So this is our scenario. But then let's try to, I know, usually we take first positive delays, then we take negative delays. So let's move to the positive range. I don't know, let's take typical values like t/2, t, maybe 2t, and so on and so forth. So we take t/2. We have to move our pulse by t/2 to the left, like this. Okay, and what will be the result? What will be the result of integral of this correlation? Exactly. Because if we look to this picture, we see that they overlap only in the range from 0 to t over 2. And what's the amplitude for both rectangular pulses in this range? It's u0. Then we get that we have u0 squared times t over 2. And then if I move further by, let's say, t, this is t, shift by t, what will be the result of correlation? 0, because simply speaking, they not overlap each other. So now we can say, or we can show these points. We have u0 squared t over 2, and we have 0. And of course, you see that the correlation linearly decrease when we increase delay. Okay, let's go to the negative range for delays. Again, I choose, I move it by minus t over 2. And again, you see that correlation, when we calculate correlation, it will be equal to 0 squared times t over 2. So overlapping range equals to t over 2. And moving further, when we come to the point minus t, we get that result equals to 0. And we can show that for negative range, we have 0 squared by t over 2 and then 0. This is how it looks like for rectangular function. Okay. This is our first autocorrelation function. Second, we take another signal. Positive rectangular pulse and then negative rectangular pulse. Change scaling a little bit. Have u0 from 0 to t over 2, and then from t over 2 to t over 4, dt over 4. This is time. So we do all the same. I copy this signal. Actually, I supposed to make it red. This is our original signal. I just copy, make copy. And I place it below. So now let me make it green. Okay, and now we have more interesting situation, because we have two rectangular pulses. Let's try to find critical points that we need to analyze or evaluate. So now we plot autocorrelation. Phi 2 of tau have 0. And let's try to think what we get for the second. So okay, if I calculate first, we start always with the point that corresponds to 0 delay. If I calculate, if I try to calculate correlation for 0 delay, what do I get? No, it's not 0. I think we have also some answers in the chat. 0 squared times t by 4. No, it's not also it's not correct. Yeah, by t. Yes, exactly. So the answer will be exactly the same as you see on the left side. Why? Because you can just consider first half of our signal. We have positive rectangular pulse times another positive rectangular pulse. So product will give us positive, and the correlation, or not correlation, but integral of this first half will be u0 squared times t by 2. Okay, but then if you go to second half, you have negative rectangular pulse times another negative rectangular pulse. Minus times minus gives you plus. As a result, for second half, integral will be equal, again, u0 squared by t by 2. And total integral will have value u0 squared times t. The same result. But then something interesting happens when we start moving our function. So if I move, I want to move this. Okay, if I move like this, it's not clear actually what happens. Let's maybe shift it slightly more and consider delay that equals to what it is. It is t. Yeah, as this delay corresponds to t. And what happens if we have delay equals to t? What will be the squared? And what's the sign? Plus or minus? Minus. Because if you look to this situation, you see that we have overlap only between positive rectangular pulse and second negative part. And then when we multiply amplitudes, we get minus u0 squared times duration of each half. It will be times t over 2. So for delay t, we have negative result, u0 squared t over 2. This is what we get. And on the other side, no, nothing. This is for, sorry? Yes, this is delay t by 2. Exactly. This is delay t by 2. This is for delay t by 2. We have negative result. And then we can actually make the following trick. We say, but wait a second, we are working with rectangular pulses. And we know that for one rectangular pulse between critical points, we have linear correlation. And here we have this one critical point when delay equals to 0, another critical point when t equals to 2. Actually, these critical points, nothing else as edges. And then what we do, we simply connect these 2 points between each other. This is how we get that actually this correlation will decrease slowly from u0 squared by times t to the point minus u0 squared t by 2. Okay, and then if we go further, and move it to the point, it should be t. It should be point corresponding t. What will be the result? 0. So at point that corresponds to t, we have 0. Okay, and we can do the same experiment considering correlation for negative delays. So our starting point. starting point, and then we start, don't rescale. But we start to move to the left by negative frequency, negative delays. And when we reach point minus t over 2, again, we get that correlation equals to minus u0 squared by t over 2. And then we come to the point minus t, correlation will be equal to 0. So for negative delays, have minus t over 2. And we have correlation minus u0 squared t over 2. Then we connect these lines, this line, and at the delay minus t, we have correlation equals to 0. That's what we get. Okay, fine. And what do we need to calculate else? We need to determine, yeah, this is all for part A. It's for question where we need to determine autocorrelation function for each signal. And also we usually specify superscript E. It means that we're working with energy signals, because when we start discussion about periodic signals, if we use the same procedure, we will get infinitely big, large correlation function. And then in order to avoid such situation, we normalize by period of our periodic signal. Okay, and now we have two correlation functions. Yeah, any questions about how we find it? Now we come to the question about energy spectral density.
Sir, basically we need to shift towards right and towards left to determine the autocorrelation function. Hello?
Could you please repeat? Because again, something wrong with microphone.
Okay. Sir, as you have done for these two signals, we need to shift towards left and towards right.
Yes,
Then we
it's
have
correct.
to compute. Then we have to compute the correlation.
Yeah, this is correct. Yeah, this is what we do.
Yeah.
Actually, when we calculate, when we analyze correlation, we simply evaluate different points for delay. You can take as many points as you want, but actually, if you work with such simple functions that we have in our course, it just comes to the points that you need to evaluate only critical points that corresponds to edges of your pulses, of your signals, yeah, or components that comprise that your signal. Yeah, this is what we do. We just simply take different delays, we shift by these delays our signal, and then we try to evaluate what's the overlapping area and what's the value for this overlapping area. This is how we calculate correlation.
Sir, and I think we can utilize one property here, like we are having two step varying signals over here in both the cases. So we have seen whenever we are convolving two step varying signals, then we will get a ramp like we are getting in both of them. So slope of the ramp is always the product of the two
Please close
amplitudes.
the microphone because I don't hear you.
Hello. Yes, sir.
Could you please speak louder and closer to microphone?
Sir, I'm saying that we have that property in signal system, like if there are two step varying signals being convolved together, then the slope of the ramp is going to be the product of the two amplitudes.
Get question. I didn't get question, but anyway, I mean.
Is my voice audible?
Yeah, maybe it's better if you type your question in the chat because I think last time we also had the same problem because we simply don't hear you. And I think it's a problem with microphone on your side, because I also remember that other participants could hear very, very well other participants. Yeah, please write in the chat, because I simply don't understand the question. Sorry for this.
Voice is not audible, sir, properly.
No, we cannot hear you.
Professor, I have one doubt.
Okay, now it's better, but it's also not good.
This is other participant, not the one who just asked before. Hello?
I don't understand what's going on. Okay, let's continue. Please write in the chat, because I simply don't understand what's happening. Yeah, otherwise we just spent the whole tutorial trying to answer questions, or yeah, anyway. So next part, that we have to find corresponding energy spectral densities. We have to find phi y1 energy of F and phi 22 superscript E of F. And I think we have hint at this point. Yes? I hope I will, yeah, I understand. Okay, yes. Yes, yeah. I mean, you could imagine that it's not necessary that you limited in time, but if you calculate energy for this signal, it will be finite. This is the point. It will be finite value for energy, but because if you take periodic signal and you simply integrate from minus infinity to infinity, result will be equal to infinity. And this is a problem that you have to somehow be able to operate. But we also can do this, but for this we normalize by period. We simply just cut one period and then just consider periodic signal within one period. And here we have only one pulse. If you integrate, you will get just finite energy. This is the point, that as far as it's finite, we call this signal as energy signal. Then it's power signal. It will be constant power, because it delivers energy with constant rate, but as far as it delivers it constantly, energy will increase with time. But power, the rate of energy, how fast you get it, will be constant. Or, I mean, at least we consider such signals where it's constant, because of course you can find signals where it also changes, power and energy, everything changes. But in our course, we consider these power signals where power will be finite. Okay, if in questions they ask to write an expression, how can we write it? This is our next question, if we want to write the expression. I mean, usually we don't ask you to calculate this autocorrelation explicitly, because otherwise you will have to calculate this integral. Yeah, you will just need to calculate. It will be. It's not difficult, because you just need to calculate this integral of scalar, get after integral t, and then you just need to set proper limits. But we don't ask you to do this. And but usually we ask you the following question. We ask you to write expression for correlation function itself, for the resulting signal that you get. And then, yeah, then you can have this such question. And this is what we're actually going to do at the moment, because we need to find energy spectral densities. And yeah, the easiest way to find is to calculate the Fourier transform of correlation function. And in order to calculate a Fourier transform, you need to have expression for correlation function itself. But for our case, again, usually we consider very simple functions, and you see that first correlation function, nothing else as triangular function. Then you can write that correlation function of tau, first correlation function, is scaled version of triangular function. And we have its function of tau, and duration of our, or denominator of our triangular function is t. Okay, fine. But what should we do for second function? And we also can use triangular, can represent this correlation function as combination of different triangular functions. Now, you do the following. You just see that if you take one triangular at position minus t over 2 is amplitude minus u0 squared t over 2, then you add triangular at origin, centered at origin, is amplitude u0 squared over t, and add third triangular at centered at t over 2 with amplitude minus u0 squared t over 2, and combine them, you will get exactly this function that we have for second correlation function. And we use it and we write that our second correlation function, tau, can be written and we write that. We just write everything what we know. Maybe I start with the triangular centered at origin, u0 squared times triangular tau, and then divided by t over 2. Okay, then we have minus. Then we write left triangular function minus u0 squared t over 2 triangular, and we have tau over, we also have to include shift, tau plus t by 2 divided by t by 2. And minus third triangular. We have u0 squared t by 2 triangular, and we have tau minus t by 2 divided by t by 2. This is expression for correlation function, second correlation function. Yes? Squared. Yeah, I forget squared.
For the, yeah.
This is how we write triangular function. So if we have triangular function with denominator t, it goes from minus t to t. But if you consider rectangular function with denominator t, it goes from minus t over 2 to t over 2. There is difference, because triangular 2 times wider than rectangular with the same denominator. And but I also can make mistake. So we have, this is that we have 1/2 t, and for second 1/2 t over 2. And now we have to calculate Fourier transform. Let's do it for first correlation function. First correlation function, we calculate Fourier transform, and we get energy spectral density. So phi y1 of f, then we write, no, but we have simple triangular function, and we have Fourier transform for triangular function. So we get t times c squared by f capital T. But we also should take into account scalar in front of it. u0 squared times t was from beginning, u0 squared times t, and then we have Fourier transform. T psi square pi f capital T. Yeah, this is what we get for first Fourier transform. Now let's take a look to the second Fourier transform. First one was very simple. For second one, we have more components. There we have to be very careful. So we write that spectral energy spectral density for second correlation function of frequency, of course. We find we have three functions, and let's do Fourier transform step by step. U0 squared times t times Fourier transform of triangular function. T over 2 times c squared pi f t over 2. Okay. Then minus u0 squared t by 2 times, we have again another triangular shape function, t over 2 times c squared pi f t over 2. But in addition, we have shift in time domain, in delay domain. Yeah. And if we look to our cheat sheet, we see that this shift in delay domain will be converted to additional phase for each frequency component in frequency domain. Minus j 2 pi and so on and so forth. Minus j 2 pi f, and then we have shift by minus t over 2. Okay, and then we have third component, u0 squared t over 2 times t over 2, it was before. Then we have t over 2 c squared pi f t over 2 times exponential function minus j 2 pi f and shift by t by 2 by 2. Fine. Now what we can do, we can see that actually in all three components we have the same part. We have c square function, we have u0 t squared by 2, and then we have something else. And the rest we can write separate. So, and by the way, let's look to exponential functions. We can move, when we move outside parentheses, all the remaining parts, inside parentheses, we have exponential function of j alpha, and we have second part exponential function minus j alpha, and we have plus. And what will be the result? Cosine function. But it will be 2 times cosine function. But also, I can say that we have 1 over 2 in front of it. And as a result, it will be just cosine of argument. So let's write the result that we get. So I move outside u0 squared t squared 1 over 2. And then inside not also psi function times psi square function pi f t over 2. And then inside parentheses, I have 1 minus cosine of 2 pi f t by 2. And how can I write cosine 1 minus cosine? Cosine itself can be written. Cosine itself can be written as cosine alpha. Be written as cosine square alpha over 2 minus sine square alpha over 2. Then 1 minus psi square sine square alpha over 2 is nothing else as cosine square alpha over 2. And we get, no, 1 second, it's wrong. It's wrong because we have minus in front of parentheses. This is CAF. It's very It's easy to make mistake. 1 minus cosine square alpha over 2 plus sine square alpha over 2. And then 1 minus cosine square is sine square alpha over 2 plus sine square alpha over 2. And we can rewrite this expression. We can write it as 1 over 2 u0 squared t squared times c square pi f e over 2 times sine squared, and then we have pi f t over 2. Pi f t over 2. I think we have comment in the chat. 2 sine square 2 times square sine pi f t over 2. Yes, exactly. And then we can actually further simplify this expression. We can further simplify this expression taking into account the following fact, that the psi function, psi pi of x, no, not sine, psi pi of x can be written as sine pi of x divided by pi of x. Yes? And you can replace this psi square function by this. Just one moment. Does it make sense? No, actually it doesn't make sense because we just have sine power of 4. No, we just keep it like this. We just keep it like this, and we can also cancel 2. We can cancel 2 and 1 over 2. So this is our energy spectral density. Okay, now we come to more interesting point. We need to make plot of each spectral density. Let's try to do this. But okay, let's write final expression. We have u0 squared t squared times psi squared pi f t over 2 times sine squared pi f t over 2. We could we could further simplify if we would have cosine instead of sine, but we have sine square and then we just keep it. Okay, so now let's make a plot of everything what we get. So it's our first function, and then we also plot second function. So 2 functions. So where is our second function? First function. It's here. Let me copy. It's our first function. So once again, I ask you the question, at which points c function will be equal to 0? What will be the first 0 point for c square function? But please answer louder because I don't hear you. Yes, 1 over t. You consider points plus minus 1 over t and then integer multiples of this 1 over t. Maybe I wider because I will make 1 over t like this. 1 over t minus 1 over t minus 1 over t. Minus 2 over t. This is our spectral density. energy spectral density. So, and this is our C square function, so it must be smooth. I specify some amplitude, not some, but amplitude u0 squared t squared for 0 point, and then I have to show very smooth function. Our C square function. It's our frequency range. Okay, now we come to second function. First function was not difficult. Second function, more interesting. Second, it's our spectral density to 2f. Equals to this. So we have to do it step by step. I propose do the following. First, we plot function c square, then we plot sine square, and at last step, we just combine these two results and try to see what we get. So we start with c square function. Okay, I have the same question. At which points this function will have zeros? 2 by t. Actually, sorry? Yes, I mean 1 over t by 2, but it will be 2 by t. So we also received the same answer in the chat. For full screen mode. 2 by t, exactly. So, and 2 by t. Probably I have to make it even wider. So now let's try to show this function. This is our c square function. And again, it must be very smooth. This is our 2 by t. By t is 2 by t and minus 4 by t. Okay, and then we have sine function. We have sine function, and at zero we have 0. Then at when we take point 2 by t, when we take frequency 2 by t, our function will be equal to 0 again. And between these 2 points, our c function, let me orange, it will be positive half, our sine function. This? But this is for sine function. And we have here sine square function. So I will show you what we have for sine function. It would be something like this. It's positive half and then negative half. Okay, but we have sine square function. As a result, we plot actually it looks like cosine function, but shifted No, sorry. It's 1 minus cosine function. Like this part. And second also will be positive. Yeah, only positive amplitudes. It's right. Get as our picture. And now we have to multiply these two functions. So we multiply our c square function and sine function. So as a result, we get this is point where it touches. Not we get something like and also so then in negative range we have the same behavior. We have this our first, and we have dot after we multiply something like this. And we can compare actually these two plots. Can compare what happens. That for rectangular pulse, this is how it looks like, and for I hope you can see this resulting red line. This red line corresponds to the final result that we have. We can say that it's our phi to superscript e of f. So we have wider spectral density, but we don't have components at 0. We don't have any DC components. And of course, because if you look to the original signal, you see that it's balanced. You have positive part and then you have negative part, and mean value will be equal to 0. No DC. So it's fine. And of course, you have DC component because for rectangular pulse, if you just calculate average, it will be non-zero. And it's exactly what we observe here. We have some non-zero DC components for first spectral density, and for second one, we don't have anything at 0 frequency. So it's absolutely fine. Okay. And then we come to the last question. We still have some time. No, we don't have time, but let's try to analyze and answer this question. We need to determine the cross-correlation function. C. Determine cross-correlation function 1, 2, E of tau. And here we do the following. You remember the definition of correlation function. This is our definition. I can copy this expression, but then I have to slightly change it. When we calculate cross-correlation between, let's say, K and M signals, we have first signal as it is, and we shift second signal, Q of M. And this expression gives you algorithm, what you should do. You should write your first signal as it is, and you should place, or you should make second signal. You should put a copy of second signal and start moving it to the right and to the left. Again, analyze what's the overlapping area between two signals. So, what was the first signal? First signal was simply a rectangular pulse, but no. First, we need to understand, we need to analyze 1, 2. cross correlation. So we take first signal, fix it, and we change second signal. So let's try implement this part. So I just repeat once again what I know. I know that our first signal is a rectangular shape function. This is our first signal with amplitude Q0 and center at T/2. Okay. Then second signal is two rectangular pulses. It comprises two rectangular pulses with different amplitudes, positive and negative. Have positive rectangular pulse, negative rectangular pulse. This is how it looks like. And amplitude Q0. So now, once again, when we take our signal and we select positive delays, we shift it to the left. When we choose negative delays, we shift it to the right. It helps us to find proper cross-correlation function. Proper cross-correlation function. And my first question, what's the value of cross-correlation for zero delay? This is so-called phi 1, 2 of tau. What's the cross-correlation for zero? No. Zero. Have the same answer in the chat. Yes, zero. Why? Again, we just take each half separately. You consider each half separately. And then if you take half from 0 to T/2, you multiply positive part by positive part of first signal. It will be a result of this integral will be U0 squared times T/2. U0 squared T/2 for second half. But for for first half. For second half, you have positive amplitude for second part of first signal and negative amplitude for second part of second signal, minus U0 squared T/2. And then combining these two parts, get that result equals to 0. For delay equals to 0. But then we start to move it to the right and to the left. So at 0, we have 0. Then we, let's say, move our signal, second signal. We move to the axis. We move it to the left by T/2. And what will be the result of autocorrelation? Oh, sorry, cross-correlation? Yes. No, no, not exactly. Check in the chat. No, it's not 0. No, it's not 0. It's not correct. We shifted by T/2. Yes, minus U0 squared by T/2 times T/2. This is our point where we analyze. It is it is T/2. And at this point, we have minus U, right below, U0 squared by T/2, minus. And in between, of course, we say that it will be just line. Okay. Then we go further. I shifted further. I shifted by T. I have shifted it by T. 0. Because you simply analyze what's the overlapping area between these two functions. They not overlap. As a result, no correlation. minus, and then at t will be 0. And then if we
Prof-
go to the, if move to the
Professor,
right,
we can't see the screen. Can you please screen share?
oh wow, sorry, I stopped sharing screen. Okay, yeah, sorry. Probably this is the reason why I received so many questions. So this is what we have. And when we go to the range of negative delays, if we consider minus t by 2, and then if we consider point minus t, it means that you shift signal to the right, and then this point corresponds to t by 2, minus t by 2. What will be the result? Is plus or minus? Will be plus u0 squared by t by 2. And then if I go further, if I shift by minus t, 0, because again, they not overlap. And between these critical points, they have linear behavior. U0 squared by 2. Now smaller than 0. This is our cross correlation function between two signals. And you see that when these two signals synchronized, they don't correlate with each other. Cross correlation equals to 0. And very often you use this property in CDMA systems because you transmit at the same time different sequences, but because they not correlate with each other, they don't produce mutual interference. And this is what we very often use for transmission. But in order to use this property, you have to synchronize sequences, because you see that if you have a small offset in delay, so these two sequences have small offset between each other, immediately you will have non-zero component presenting cross correlation, just to produce you more noise. Okay, are there any questions before we stop our tutorial for today? Doubts, comments? If not, then I also have to say that next week we don't have tutorial because I will be at conference, but I will prepare recording of lecture and I place it on Moodle. For this reason, you don't need to come to lecture hall. Or we announce it in Moodle, and then it happen this time next week. Okay? So thank you for your attention, and I hope to see you in 2 weeks here. Thank you and goodbye.